So now we want to talk about entropy within the context of chemical systems and chemical reactions. So every time you do any sort of chemical change, or a physical change, anytime you're changing a chemical system, there's always an associated change in entropy, which we call delta S. So delta still means change. And so for a given chemical reaction, delta S can either be positive or it can be negative. Right? And so the sign of delta S is going to give us a lot of information and describe the change between the reactant molecules and the product molecules. And if delta S is greater than 0, that means the process of doing the reaction increases the disorder. Your product molecules are more disordered than the reactant molecules. Your product molecules have more arrangements. There's less predictability in the product compounds that you've made, in their kind of physical state and all of that. Whereas if delta S is less than 0, then that means the products have less disorder, right? And this is, when we talk about the kind of disorder in a chemical system, we're talking about it inherently in kind of the sample that you're looking at. The molecules, is it a liquid, is it a solid, all that kind of stuff. What's its temperature, all those sorts of things. So when we before we get, into doing chemical reactions, we'll start with something a little more simple and look at phase changes. Because when we look at phase changes, we're not changing the chemical at all, right? It's the exact same compound or element, whatever that we're looking at. What we're changing is that sort of relative position of atoms or molecules that make up the thing. So we know we have solids, nice ordered, all the molecules are touching. Liquids, the molecules are also touching, but they're moving freely. And then in solids, all the rules are gone. And so this idea of, if we think about solids, we have, ordered structure. We have the idea that these molecules are all touching each other. And that makes that the most predictable system. Because one of the things that we can think about is, if I know that I have an atom or molecule in my solid right here, I know all the other molecules are touching it. And I know that there's a pattern of those molecules in the solid. It's that sort of regular repeating pattern. So I know if I have a molecule right there, that means the rest of my molecules are nearby. It makes the system more predictable. There are fewer arrangements because the molecules take on a repeating pattern, right? They form this nice repeating pattern where all the molecules are kind of fit together perfectly. So solids are very predictable. When I go to a liquid, I still know, hey, I got a liquid molecule right here. All the other liquid molecules are still going to be close by. I don't know their exact position, but I know they're close by. So it's a little more disordered than the liquid because the molecules can move freely, they can flow over each other, but you certainly know that the molecules are all still close together, they're all still touching, right? You don't know their shape, but you do know the volume. Then for gas, you know basically nothing. If you know a gas molecule is right here, you don't know any information on the positions of every other molecule. In order to figure out the entire collection of gas molecules, you would need to find every single one of them. Just like, if you want to find a particular piece of garbage, you need to know where all of it was in the big pile. These cases are where, say, you have that sort of confirmed volume. You know where all the molecules are. You don't have to search through the entire flask. They're all on the bottom, right? The same idea that if you put all your pots in a particular cabinet, you only have to look in that cabinet to find the pots. And so whenever you're going through a phase change, solid to liquid is an increase in entropy, and liquid to gas is also an increase in entropy. The relative difference, there is always an increase there. The difference from liquid to gas is huge. The difference from solid to gas is smaller, right? There is some difference, but it is more disorder in a liquid, but not that much. In a gas, it's just way, way more disorder. Right? You can tell that they're just all over the place, and they're moving faster. So if you know where a molecule is right now, it's probably not going to be there in, say, a second, right? It's going to be far away because they just fly around. So now what we want to get some practice in is predicting the sign of delta S for some chemical reactions. And so for now, we're only going to be looking at the sign. We will eventually calculate numbers. But one of the things kind of fundamentally, we want to get some practice looking at the disorder of different related chemical systems. We can also use these techniques to check those answers we get later on. If you compute a number for delta S, does the sign kind of line up with what you would have predicted initially? So we're going to start with this, get kind of some fundamental understanding, and then we can also use it later as we do more quantitative approach. So our first thing we're looking at is H2O liquid becoming H2O solid. This is a phase change. And actually, in general, when we're looking at doing kind of predicting entropy, it's really going to be all about the phases, because that's where you have these big changes in the relative disorder. So H2O liquid becoming solid, that's freezing of water. Liquid to solid is a decrease in disorder. Liquids, the molecules can move, right? These molecules are touching but moving. These molecules are touching and not moving. So that means there's less disorder. Delta S is going to be negative for this process. That is always true for freezing. In every single freezing, delta S is negative. So now NaCl solid becoming NaCl aqueous. We've seen this before. This is dissolving. And so again, we're changing the phase. We're not changing the atoms or the compound or anything that's involved. We're just changing the phase. And in this case, when I go from solid, that is, not a lot of motion touching each other, now I go to aqueous. And so we haven't talked about aqueous in this about entropy yet, but if we think about it, we said that means it's dissolved in water. These are just ions just kind of floating around in water like a liquid. So when you dissolve something, it takes on the entropy of like a liquid. So in this case, you're going from solid to dissolved. That is going to be more disorder. So delta S is greater than 0. Dissolving solids always corresponds to an increase in disorder. We want to be careful, though, not all dissolving, because if I have, say, CO2 gas becoming CO2 aqueous, that would be going from gas to like a liquid, which would be less disorder. Gas is always going to be king. Gas phase is always the highest entropy by a big margin. And so when you go down, if you dissolve those CO2 molecules, they're now just floating around in the water. They're not moving freely. They are restricted to being inside somewhere in the water. So that's going to be a decrease in entropy. If we then look at this last one, I have C7H16 liquid plus 11O2 becomes 7CO2 and 8H2O. So here I have an actual chemical change. This isn't just a phase change. I got liquid and gas reacting to make gas and gas. And that's really what I want to focus in on. I basically look at what is the total change in gas molecules. So in my reactants, I have some liquid, so that's really relatively low entropy. I have 11 gas molecules, so I would have to be destroying those, right? These are reactants, so those are going to go away, but I'm making 7 plus 8, 15 new gas molecules. So I have more gas on the product side. That means there's more disorder, right? I do have to destroy 11 gas molecules. That'd be a loss of disorder, but I'm making more. I'm making 15, so I can have a net increase of 4 gas molecules. Delta S would be positive. If you're dealing with kind of phase changes, things up here, smaller changes, you can look at the relative phases. If you ever have just an overall chemical equation, you just count gas molecules. Product gas minus reactant gas, delta S follows the same sign. And that's the same rules as reactions that do work, if you remember. So delta S is positive when the work of the reaction is negative. Participation 1028, question 2. Predict the sign of delta S for each of the following chemical processes. A, CO2 solid becomes CO2 gas, and B, C3H8 gas plus 5O2 gas yields 4H2O gas and 3CO2 gas. This is the second question on participation 1028 due Tuesday, October 28th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, predict the sign of delta S for each of the following chemical processes. A is the sublimation of carbon dioxide, as shown in the picture, dry ice on the spoon. And B is the combustion of propane, as shown in the picture of the flame coming out of the burner. So the final way you can affect the entropy of a chemical system is to change the temperature. So if you have, say, some water, it doesn't undergo any chemical reaction, but you just change its temperature, that also does affect the entropy of that sample. So at higher temperatures, molecules move faster. So at low temperatures, molecules are still moving, but there's kind of less motion. Whereas as you get to higher temperatures, there is more disorder because the molecules are moving more. We can kind of see here, it's all about that predictability, right? So I know there's a molecule right here, okay, right next to it, because the molecules aren't moving a lot. I know that there's likely a molecule somewhere right here. But if I look at this high motion, this molecule is somewhere kind of in this range. And if I want to think about where its neighbor is, well, it's going to be, again, somewhere kind of in this ballpark, kind of this long region, right? There's bigger regions where each molecule could be found. There is lower predictability. There's a lot more arrangements when things are bouncing around kind of rapidly. So increasing the temperature of something always increases the entropy of that object. When we're talking about changing the entropy by changing the temperature, as we increase the temperature, the relative change in entropy decreases. Because basically the kind of change in entropy is related to the proportional change in temperature. So if you were, say, to the change in entropy of going, say, 100 Kelvin, so cold, to 150 Kelvin, still quite cold. But that is a huge relative change in the relative motion, right? Molecules barely moving, molecules moving. And then whereas at 500 Kelvin, molecules are moving real fast. So there's already really low predictability. Making the molecules move even faster doesn't really decrease the predictability. So increasing the temperature, say 50 Kelvin or 50 degrees Celsius, doesn't always have the same effect on the relative kind of change in entropy. Instead, it's a proportional difference. So, but once it basically what that means is when you get to high temperatures already, it's harder to further increase the entropy or the disorder of your system by adding in more energy as heat, warming it up even more. It's just difficult to do. It's already disordered. It's hard to make it even more disordered. All right, 2 questions on participation 1028. It's the 4th video. We are halfway through this set of videos. See you in the next one.